Airlift reactor. An airlift reactor differs from the bubble column bioreactor by the presence of draft tube, which provides better mass and heat transfer efficiencies. Airlift fermenters are, however, more expensive to construct than the bubble column reactors. There are several designs for airlift fermenters, although most commonly used design is one with central draft tube. The main function of the draft tubes are to increase mixing through the reactor. The draft tube enhances axial mixing throughout the whole reactor, reduce bubble coalescence, circulation occur in one direction, and hence bubbles also travel in one direction, which reduce bubble coalescence. Small bubbles lead to an increased surface area for oxygen transfer. It also equalizes shear forces throughout the reactor, and these are believed to be the major reason why airlift bioreactors have higher productivities than the stir tank reactors. Air riser and downcomers. An airlift reactor is divided into three regions: the air riser, downcomer, and disengagement zone. The region in which bubbles are sparse are called the air riser. The air riser may be on the inside or outside of the draft tube. The latter design is preferred for large scale fermenters as it provides better heat transfer efficiencies. Rising bubbles in the air riser cause the liquid to flow in a vertical direction. To counteract these upward forces, liquid will flow in a downward direction in the downcomer. This leads to liquid circulation and thus improve mixing efficiency as compared to bubble columns. The enhanced liquid circulation also causes bubbles to move in a uniform direction at a relatively uniform velocity. This bubble flows pattern reduces bubble coalescence and thus results in a higher oxygen transfer rate as compared to bubble column. The role of disengagement zones are to add volume to the reactor, to reduce foaming, and to minimize recirculation of bubbles through the downcomer. The sudden widening at the top of the reactor slows the bubble velocity and thus disengage the bubbles from the liquid flow. Carbon dioxide rich bubbles are thus prevented from entering the downcomer. The reduced bubble velocity in the disengagement zone also leads to reduction in the loss of medium due to aerosol formation. Increase in the area will also help to stretch bubbles in foams, causing the bubbles to burst. Axial flow circulation caused by the draft tube also helps to reduce foaming.